Hello. Hello. Oh. Hello, everybody. It's me again. I'm gonna pick up where I left off. I had to move spots because that reflection was getting on my nerves. So you're now in my office. Enjoy the vibe. But here we're gonna continue on with our discussion of conditional derivation. Now remember, conditional derivation. It's a derivation strategy used to derive conditionals. It's essentially our way of getting around not having a basic derive or like a basic rule or direct inference rule that allows us to introduce conditionals. And so again, you only see it when you have situations in which I've asked you to show something whose main connective is a conditional right there. So here's an example. I want to show you another example. You have plenty of examples in hard degree in the textbook to walk through this, but again, it's not a bad idea to walk through some directly here. What I want you to do here is to show that if R, then P or S. Okay, I get it. You're already freaking out. You're like, bro, there's no R. There's no R here. There's no S. What am I supposed to do? I hear you. Calm down. Let's take a breath. A bit of meditation. Remember what you do whenever you see the main connective that you need to prove being a conditional. Next line. You assume the thing the arrow is pointing from, the R. You assume that. Next line. Show P or S. You try to show the thing that the arrow is pointing to. Now, I hear you. Okay, we got the R. Good deal. How do we get P or S? All right, now let's think about what we have. You've got a P and you've got a Q. You've got P and Q. All right, no S for sure. Remember though, we have a way of introducing disjunction. It's disjunction introduction. It allows us, whenever we have a letter, to introduce or and whatever other letter we want. We also have a P, right? So here's what we do. Line 5. You got to break the P out here. So P, you infer that. How do we do that? Conjunction elimination. So that's line 1. Conjunction elimination. Remember conjunction elimination, you just need the one line, you get one output. So you just need the justifier by cite one line. That's line 1. You get P justified. Line 6, P or S. You can introduce whatever you want. Anything. P or S. S is nowhere near in the premises. That's fine. You can introduce it. It doesn't matter. That's how the rule works. The rule says if you have a letter, you can introduce a disjunction and introduce any other letter you want, anything you want. That is sufficient to show P or S. And now we did that. Don't let me miss this part. That was a direct derivation. Direct, we just used the proof rules, disjunction elimination, conjunction elimination here. Now once we did that, we were able to prove everything under this show line on the condition of R. And so we've demonstrated that if R, then P or S. And that was what we were trying to show. Dun, 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 dun. So what I've highlighted here in conditional derivation is not just that you can derive, introduce conditionals, you can prove conditionals are true. But also here, pay attention to the direct rules they have, those 7 basic rules you have. Pay attention. Sometimes they're surprising, right? You can literally introduce whatever you want in a disjunction. That's just how the rule works. The rule works just like that. If I'm looking at the meta characterization of it, you can just introduce, I don't know, any other Greek letters? Beta. Beta did not appear previously. You can introduce chi, introduce whatever, alpha, whatever, or gamma, or whatever that is. Whatever you want. That's just how the rule works. Again, because if phi is true, then phi or whatever is true. Remember, truth preservation. Now, sometimes I'm going to ask you to prove things from no premises. Typically, so far, I've been giving you premises, show me stuff. Not now. Sometimes, I just want to be able to prove things from no premises. what you'll find when you see this, you always see it, and it'll look something like just this, and then you'll just have the thing to prove, listed here. So just one line, the first line. Now, a couple of things to point out. One, again, no premises to pull from. Two, this expression, if I've asked you to prove something from no premises, and you can do it, this is a tautology. It's a tautology. If you plug in a truth table, it would always be true. I'm gonna do it. The main connective is here. You know, true, 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 or true, true, false, false, true, false, true, false. What do we got? True, true, false, false. Same here. True, true, false, false. True, false, true, false. What do we get? True, true. What do we get? True, true, false there. True. Is that connective? Now we're comparing true, 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 false, 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 false. Main connective. Tautology. Every time, if you can prove something from no premises, it is a tautology. It is always true. Remember, keep this in mind. Remember what I said earlier about taking arguments, like valid arguments, and then converting them into tautologies. So here's an example. I'm just going to give you if P and Q. This is one of our proof rules, right? This is an instance of conjunction elimination. If you have P and Q, then you can infer P. And what I say, you can run this through a truth table, and there's a trick. P and Q, right? You just essentially replace this bar with a conditional, and you bunch this up. And if you had more premises, you just join them up with conjunction. Remember, true, true, false, false, true, true, false, false, right? True, false, true, false, true and true, true, true and false, 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 right? Well, true, 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 false, false, false. Anytime the first part of the conditional is false, the whole thing is true. So true, true, true. Tautology. This proof rule, or an instance of it here, is that when you've bunched it up into this form, when you've converted it into this form, is a tautology. Anything you can prove, anything you prove in our language, if you bunch it up that way, if you combine all the premises into conjunctions, and then you put a material conditional between that set of conjunctions and the thing I ask you to show, that is always a tautology. So think about it. If you take all of the premises and you conjoin them all together, you put a conditional between them and the conclusion, it's a tautology. Consider the following. Suppose I said, prove to me this. I could easily do it. P is right there. We could also say that should be true too, right? So you should be able to easily derive this. In fact, I'll just tell you how. There's a rule called repetition. We'll give it an R. From a premise, just infer from phi, because it's truth preserving. If phi is true, then phi is true, right? Now, you could just do that here, P. Now, take all this, bunch it up, which is essentially what I've done here. Now, I'm going to move it over so it's a little closer to me. P and Q. P. I'm going to give myself a little more room. One show line. I'm saying, as I was pointing out here, this will be a tautology if I can prove it. And if I can prove it, I can derive it from no premises, right? Now, how do I do this? So I'm going to do that. I'm going to do the easier one, huh? First thing I do, line 2, assume P and Q. And this is for our conditional derivation. And then show P. And how do you do it? Easily. All you got to do is break the conditional apart, right? And then you get P. And that's 2, conjunction, elimination. Boom, boom, mark out, done. On the condition, no premises. And what did I say about removing the show line? That means it's added to your premises. So this, P, if P and Q, then P, it's just true. It's always true in any argument. Whether it's part of the premise set or not, it's always implicitly part of the premise set because you don't need any premises to prove it. And again, it lines directly up with our proof rules, lines directly up with that method for like constructing tautologies out of good arguments, valid arguments. Again, you can run that all the way back here where we started. I show if P, then if Q, then P. First thing you do, assume P. Second thing you do, show if Q, then P. Uh-oh, another conditional. Every time you see a conditional in a show line, assume the thing the arrow is pointing from and show the thing it's pointing to. Now, how do we do that? Just introduce to you a rule, repetition. R from any phi. Phi. You can infer phi. From P, you can infer P. And we'll just cite that as 2R. I boxed that proof up and I've shown P. I also showed that on the condition of Q, I can get P. Right? I did that by conditional derivation. And then I showed that if I assumed if P, or P, that I could prove if P, then if Q, then P. Also from conditional derivation. And that is it. And now, effectively, I've just shown that it is always true in any argument if P, then if Q, then P. Just like a minute ago, I showed it is always true in any argument if P and Q, then P is true. We can do this again and again and again. What I want to show you something is something else a little more complicated. I'm going to pause right now. This will be fun.